That's all right. So welcome back. Today we're gonna cover the debugging and profiling. Before I get into it, we're gonna kind of make another reminder to fill in the survey. Just one of the main things we want to get from you is questions, because the last day is gonna be questions from you guys about like things that we haven't covered that or like you want us to kind of talk more in depth. And the more questions we get, the more interesting we can make that section. So please go on and fill in the survey. So today's lecture is going to be a lot of topics. All the topics revolve around the concept of what do you do when you have a program that has some bugs, which is most of the time. Like when you're programming, you're kind of thinking about how you implement something, and there's like a half-life or like fixing all the issues that like program has. And even if your program behaves like you want, it might be that it's really slow or like it's taking a lot of resources in the process. So today we're going to see a lot of different approaches of dealing with these problems. So the first section is on debugging. Debugging can be done in many different ways. There are all kind of like the most simple approach that like pretty much like CS students will go through will be just you have some code and it's not behaving like you want. So you probe the code by like adding print statements, and this is called printf debugging. And it works pretty well. Like I have to be honest, like I use it a lot of the time because how kind of simple to set up and how quick the feedback can be. One of the issues with like printf debugging is that you can get a lot of output, and maybe you don't want to get as much output as you're getting. And people have thought like slightly more complex ways of doing printf debugging. And make this. There we go. And one of these ways is kind of what is usually referred to logging. So the advantage of doing logging versus doing printf debugging is that when you're creating logs, you're not necessarily creating the logs because there's like a specific issue you want to fix. It's mostly because you have built a more complex software system and you want to log when some events happen. And one of the core advantages of using a logging library is that you can define severity levels, and you can filter based on those. And let's see an example of how can we do something like that. So yeah, everything fits here. This is really silly example. We're just gonna sample random numbers, and depending on the value of the number that we can interpret as a kind of how wrong things are going, we're gonna log the value of the number, and then we can see what is going on. And let me check I need to disable this from errors. And if we were just to execute the code as it is, we just get the output and we just keep getting more and more output. But like you have to kind of stare at it and make sense of what is going on. And we don't know what is the relative timing between printfs. We don't really know whether this is just an information message, of like a message of whether something went wrong. And if we just go in and undo, not that one, but I want to undo that one, we can set that formatter. And now the output looks something more like this. So for example, if you have several different modules that you're programming with, you can identify them with like different labels. Here we have debug levels, we have critical info, different levels. And it might be handy because here we might only care about the error messages. Like those are like we have been working on our code, so far so good, and suddenly we get some error. We can log that to identify where it's happening, but maybe there's a lot of information messages. But we can deal with that by just changing the level to error level. And now if we run this again, we're only going to get those errors in the output, and we can just look through those to make sense of what is going on. Another really useful tool when you're dealing with logs is, as you kind of look at this, it has become easier because now we have kind of these critical and error labels that we can quickly identify. But since kind of humans are fairly visual creatures, one thing that you can do is use colors from your terminal to identify these things. So now, changing the formatter, what I've done is kind of slightly change how the output is formatted. And when I do that, now whenever I get a warning message, it's color-coded by yellow. Whenever I get like an error, it's like fade red. And when it's like critical, I have like a bold red indicating something went wrong. And here is like a really short output, but when you start having like thousands and thousands of lines of log, which is not unrealistic and happens every single day in a lot of apps, kind of quickly browsing through them and identifying where like the error, like the red patches are, can be really useful. A quick aside is you might be curious about how the terminal is displaying these colors. Like at the end of the day, the terminal is only outputting characters. So how is this program, or like how are other programs like LS that like has all these fancy colors? How are they telling to the terminal that it should use these different colors? This is nothing kind of extremely fancy. What these tools are doing is doing something along these lines. Here we have a command. I can clear the rest of the output so we can focus on this. There's some special characters, some escape characters here. Then we have some text, and then we have some other special characters. And if we execute this line, we are like red, this is red. And you might have picked up on the fact that we have a 25500 here, and this is just telling the RGB values of the color we want in the terminal. And you pretty much can do this in any piece of code that you have, and that you can color code the output. And your terminal is fairly fancy, supports a lot of different colors in the output. This is not even all of them, this is like a 16 of them. And I think it can be fairly useful to know about that. Another thing is maybe you don't enjoy, or like you don't think like logs are kind of really fit for you. The thing is, a lot of other systems that you might start using will use logs. As you start building larger and larger systems, you might rely on other dependencies. Common dependencies might be web servers or databases is a really common one. And those will be logging their errors or like exceptions in their own logs. Of course, you will get some client-side error, but those sometimes are not like informative enough for you to figure out what is going on. In most Unix systems, the logs are usually placed under a folder called like /var log. And if we list it, we can see there's like a bunch of logs in here. So let me scroll a little bit. So we have like the SATA monitor log, like some wiki logs, things related to the Wi-Fi, for example. And if we output the system log, which contains a lot of information about the system, we can get information about what's going on. Similarly, there are kind of tools that will let you more like sanely go through this output. But here, looking at the system log, I can look at this and say, oh, there's some service that is kind of existing with some abnormal code, and based on that information, I can go and try to figure out what's going on, like what's going wrong. One thing to know when you're working with logs is that more traditionally, kind of their own, like every software had their own log, but it has been increasingly more popular to have a unified system log where everything is placed. And you can, like pretty much any application can log into this system log, but instead of being in a plain text format, it will be compressed in some special format. An example of this was what we covered in the data wrangling lecture. In the data wrangling lecture, we were using the journal CDL, which is kind of accessing the log and outputting all that output. Here in Mac, now the command is log show, which will display a lot of information. I'm gonna just display the last 10 seconds because logs are really, really verbose. And just displaying the last 10 seconds is still gonna output a fairly large amount of lines. So if we go back through what's going on, we here see that like a lot of Apple things are going on since this is a MacBook, and maybe we could find errors about like some system issue here. Again, they are fairly verbose, so you might want to practice your data wrangling techniques here, like 10 seconds equal to like 500 lines of logs, so you can kind of make an idea of how many per second you're getting. And they're not only useful for figuring out some other programs output, they're also useful for you if you want to log there instead of into your own file. So using the logger command in both like in Linux and Mac, you can say, okay, I'm gonna log these hello logs into this like system log, and we execute the command, and then we can check by going through the last minute of logs, since it's gonna be fairly recent, and grepping for that hello. And we find their entry, fairly recent entry, that we just created that said hello logs. And as you become more and more familiar with these tools, you kind of will find yourself using the logs more and more often. Since even if you have like some bug that you haven't detected and the program has been running for a while, maybe the information that is already in the log can tell you enough to figure out what is going. However, printf debugging is not everything. So now I'm gonna be covering debuggers, but first, any questions on logs so far?
So what kind of things can you figure out from the log? Like this hello logs, it says that you did something with hello at that time, or?
Yeah, like say, for example, I can write a bash script that like the text, well, like it checks every time what the Wi-Fi network I'm connected to. And every time it detects that that has changed, makes an entry in the logs and says like, oh, now we have changed Wi-Fi networks. And then you might want back and parse through the logs and check like, okay, when did my computer change from one Wi-Fi network to another? And this is just kind of like a simple example, but there are many ways, many types of information that you could be logging here. More commonly, you will probably want to check, like if your computer, for example, is entering sleep, for example, for some unknown reason, or like something like hibernation mode. There's probably some information in the logs about who asked that to happen, or like why is that happening. Any other questions? Okay, so when printf debugging is not enough, the best alternative after that is using, let me exit that and low. So he is using a debugger. So a debugger is kind of a tool that will wrap around your code and will let you run your code, but it will kind of keep control over it. So it will let you kind of it will let you step through the code and execute it and set breakpoints. And you probably have seen debuggers in some way if you have ever used something like an IDE, because IDEs have this kind of fancy, set a breakpoint here, execute. But at the end of the day, what these tools are using is just these command line debuggers, and they're just presenting them in a really kind of fancy format. Here we have kind of a completely broken bubble sort, simple sorting algorithm, don't worry on the details. But we just want to sort this array that we have here. And we can try doing that by just doing Python bubble. And when we do that, say, oh, there's some index error, list index out of range. We could start adding prints, but as if we have like a really long string, we can get a lot of information. So how about we go to the moment that we crashed? Like we can go to the moment and examine what the current state of the program was. So for doing that, I'm gonna run the program using the Python debugger. Here I'm using technically the IPython debugger just because it has nice coloring syntax, so it's probably easier for both of us to understand what's going on in the output, but they are pretty much identical in any way. So we execute this, and now we are given a prompt. We are being told that we are here at the very first line of our program, and we can, L stands for list. So as with many of these tools, this kind of like a language of operations that you can do, and they are often like mnemonic, as it was the case with Beam or with Emacs. So here L is for listing the code, and we can see the entire code. S is for step, and will let us kind of one line at a time go through the execution. The thing is, we're only triggering the error sometime later. So we can restart the program, and instead of trying to step until we get to the issue, we can just ask for the program to continue, which is the C command. And hey, we reached the issue. We go to this line where everything crashed. We're getting this list index out of range. And now that we are here, we can say, okay, first, let's print the value of the array. So this is the value of the current variable array. Okay, it doesn't, so we have 6 items. Okay, what is the value of j here? So we look at the value of j. J is 5 here, which will be the last element. But j plus 1 is going to be 6. Oh, so that's triggering the out of bounds error. So what we can do, we have to do is this n instead of n has to be n minus 1. Like we have identified that the error lies there. So we can quit, which is Q, again, because as a post-mortem debugger. And we go back to the code and say, okay, we need to append this n minus 1. Okay, that will prevent the list index out of range. And if we run this again without the debugger, okay, no errors now, but this is not our sorted list. This is sorted, but it's not our list. Like we're missing entries from our list. So there's some behavioral issue that we're reaching here. Again, we could start using printf debugging, but kind of a hint now, that's probably the way we're swapping entries in the bubble sort program is wrong. And we can use the debugger for this. We can go through to the moment we're doing a swap and check how the swap is being performed. So a quick overview. So we have a kind of 2 for loops, and in the most nested loop, we are checking if the array is larger than the other array. Thing is, if we just try to execute until this line, it's only going to trigger whenever we make a swap. So what we can do is we can set a breakpoint in the 6th line. We can create a breakpoint in this line, and then the program will execute, and the moment we try to swap a variable is when the program is going to stop. So we create a breakpoint there, and then we continue the execution of the program. The program halts and say, hey, I have executed and I have reached this line. Now I can use locals, which is kind of a Python function that returns you a dictionary with all the values to quickly see the entire context. Say, okay, the string, the array is fine, n is 6, okay, I'm just at the beginning, and I step, go to the next line. Oh, and identify the issue. Like I'm swapping one item at a time instead of simultaneously. So that's what's triggering the fact that we're losing variables as we go through. And that's kind of like a very simple example, but debuggers are really powerful. Most programming languages will give you some sort of debugger. And when you go to more low-level debugging, you might run into tools like, you might want to use something like, where is this? Oh, sorry. Like GDB. And GDB has one nice property is GDB works really well with C, C++, and like all these C languages. But GDB actually lets you work with pretty much any binary that you can execute. So for example, here we have sleep, which is just a program that's going to sleep for 20 seconds. And it's loaded, and then we can do run, and then we can interrupt this, sending an interrupt signal. And GDB is displaying for us here like very low-level information about what's going on in the program. So we're getting the stack trace. We're seeing like we're in this nano sleep function. We can see the value of like all the hardware registers in our machine. So you can get a lot of like low-level detail using these tools. And I think that's all I want to cover for debuggers. Any questions related to that? Another interesting tool when you're trying to debug is that sometimes you want to debug as if your program is a black box. So like you maybe know what the internals of the program are, but at the same time, your kind of your computer knows whenever your program is trying to do some operations. So this is in Unix systems, there's this notion of like user level code and kernel level code. And when you try to do some operations like reading a file or like reading the network connection, you will have to do something called system calls. And you can get a program and go through those operations and ask what operations did this software do. So for example, if you have like a Python function that is only supposed to do a mathematical operation and you run it through this program and it's actually reading files, why is it reading files? It shouldn't be reading files. So let's see, we have, this is stray, so for example, we can do something like this. So here we're gonna run the ls minus l, and then we're ignoring the output of ls, but we're not ignoring the output of strays. So if we execute that, we're gonna get a lot of output. And this is all the different system calls that this ls has executed. You will see a bunch of open, you will see fstat, and for example, since it has to list all the properties of the files that are in this folder, we can check for the lstat call. So the lstat call will check for the properties of the files, and we can see that effectively like all the files and folders that are in this directory, they're being accessed through a system call through ls. Interestingly, is like sometimes you actually don't need to run your code to figure out that there's something wrong with your code. And like so far we have seen kind of ways of identifying issues by running the code, but what if you can look at a piece of code like this, like the one I have shown right now in this screen, and identify an issue. So for example, here we have some really silly piece of code, defines a function, prints a few variables, multiplies some variables, sleeps for a while, and then we try to print bus. And you could try to look at this and say, hey, bus has never been defined anywhere. Like this is a new variable, like, oh, you meant to say bar, but you just mistyped it. Thing is, if we try to run this program, it's gonna take 60 seconds because like we have to wait until this time sleep function finishes. So here sleep is just for kind of motivating the example, but in general you might be loading a data set that takes really long because you have to copy everything into memory. And things there are programs that will take source code as input, will process it and will say, oh, probably this is wrong about this piece of code. So in Python, this is called, like in general, these are called static analysis tools. In Python, we have, for example, PyFlex. And if we get this piece of code and run it through PyFlex, PyFlex is gonna give us a couple of issues. First one is the one, like the second one is the one we identified, like here, there's a non-defined name called bus. You probably should be doing something about that. And the other one is like, oh, you're redefining the foo variable name in that line. So here we have a foo function, and then that we're kind of shadowing that function by using a loop variable here. So now that foo function that we defined, it's not accessible anymore. And then if we try to call it afterwards, we will get into errors. And there are other types of static analysis tools. MyPy is a different one. MyPy is gonna report the same two errors, but it's also kind of complain about type checking. So it's gonna say, oh, here you're multiplying an int by a float. And you should, like, if you care about the type checking of your code, you should not be mixing those up. It can be kind of inconvenient, kind of having to run this, look at the line, going back to your beam and kind of figure out like your editor and figuring out like what the error matches to. And there are already solutions for that. And the way is that you can integrate most errors with these tools. And here, you can see there's like some red highlighting on the bus. And if we read the last line here, say no, undefined name bus. So as I'm editing this piece of Python code, my editor is gonna give me feedback about what's going wrong with this. Or like here, I have another one saying like, oh, the redefinition of unused foo. And even there are some stylistic complaints. So, oh, I will expect 2 empty lines. So like in Python, you should be having like 2 empty lines between like a function definition. There is like a research on the lecture notes about pretty much like static analyzers for a lot of different programming languages. And there are even standard analyzers for English. So I have my notes for the class here, and if I run it through this static analyzer for English, there's write good, it's gonna complain about some stylistic properties. So like, oh, I'm using very, which like it's a wizard word and I shouldn't be using it, or quickly can weaken meaning, for example. And you can have this for spell checking or for a lot of different types of stylistic analysis. Any questions so far? Oh, I forgot to mention, depending on the task that you're performing, there will be different types of debuggers. For example, if you're doing web development, pretty much all, I think like both Firefox and Chrome have a really, really good set of tools for doing debugging for websites. So here, if we go and say inspect element, we can get I don't really know how to make this larger now that I think of it, but we're getting like the entire source code for the web page for the class. What? Control plus for the human. Oh yeah, there we go. Is that better? And we can actually go and like change properties about the code. So we can say like we can edit the title and say this is not a class on debugging and profiling. And now the code for the website has changed. And this is one of the reasons why you should never trust any like screenshots of websites, because like they can be completely modified. And you can also modify the style. Like here I have things using the dark mode preference, but we can alter that. Like because at the end of the day, the browser is rendering this for us. And we can check the cookies, but there's like a lot of different operations. There's also like a built-in debuggers for JavaScript, so you can like step through JavaScript code. So kind of the takeaway is, depending on what you are doing, you will probably want to search for what tools programmers have built for them. Okay, now I'm gonna switch gears and stop talking about debugging, which is kind of finding issues with the code related to kind of more the behavior, and then start talking about like how you can use profiling. And profiling is how to optimize the code. And it might be because you want to optimize the CPU, the memory, the network. There are many different reasons that you want to be optimizing. As it was the case with debugging, the kind of first order approach that a lot of people kind of have experienced already is, oh, let's use just printf profiling, so to say. Like we can just take, let me make this larger. We can take the current time here, then we can check, we can do some execution, and then we can take the time again and subtract it from the original time. And by doing this, you can kind of narrow down and fence down different parts of your code and trying to figure out what's the time taking between those two parts. And that's good, but sometimes can be interesting, the results. So here we're sleeping for 0.5 seconds. And the output is saying, no, it's 0.5 plus some extra time, which is kind of interesting. And if we keep running it, we see there's like some small error. And the thing is here, what we're actually measuring is what usually referred to as the real time. Like real time is as if you get like a clock and you start it when your program starts and you stop it when your program ends. But the thing is, in your computer, it's not only your program that is running, there are many other programs running at the same time. And those might be the ones that are taking the CPU. So to try to make sense of that, you will see a lot of programs using the terminology that is real time user time and system time. Real time is what I explained, which is kind of the entire length of time from start to finish. Then there is like the user time, which is the amount of time your program is spent on the CPU doing user level cycles. So as I was mentioning, in Unix, you can be running user level code or kernel level code. And system is kind of the opposite. It's the amount of CPU, like the amount of the time that your program is spent on the CPU executing kernel mode instructions. So let's solve this with an example. Here, I'm gonna time, which is a command, like this cell command is gonna get these 3 metrics for the following command. And then I'm just grabbing a URL from a website that is hosted in Spain. So that's gonna take some extra time to go there and then go back. And if we see here, if we were to we have like a 2 prints between like the beginning and the end of the program, we could think that like this program is taking like 600 milliseconds to execute. But actually, most of that time was spent just waiting for the response on the other side of the network. And we actually only spent 16 milliseconds at the user level and like 9 seconds. So in total, 25 milliseconds actually executing URL code. Everything was just waiting. Any questions related to timing? Okay, so timing can become still tricky. It's also kind of a black box solution. Or if you start adding print statement, it's kind of hard to add print statements with time everywhere. So programmers have figured out better tools. These are usually referred to as profilers. One quick note that I'm gonna make is that profilers, like usually when people refer to profilers, they usually talk about CPU profilers because they're like the most common, identifying where like time is being spent on the CPU. And profilers usually come in kind of 2 flavors. There's like tracing profilers and sampling profilers. And it's kind of good to know the difference because the output might be different. And tracing profilers kind of instrument your code so they kind of execute with your code, and every time your code enters a function call, they kind of take a note of it. It's like, oh, we're entering this function call at this moment in time, and they keep going, and once they finish, they can report you, oh, you spent this much time executing in this function, and this much time in this other function, so on and so forth, which is, for example, the example that we're going to see now. Another type of tools are sampling profilers. The issue with tracing profilers is they add a lot of overhead. Like you might be running your code and having this kind of profiler next to you making all these counts will hinder the performance of your program, so you might get counts that are slightly off. So sampling profiler, what it's gonna do is gonna execute your program, and every 100 milliseconds, 10 milliseconds, like some defined period, it's gonna stop your program, it's gonna halt it. It's gonna look at the stack trace and say, oh, like you are right now in this point in the hierarchy, and it's identify which function is gonna be executing at that point. And the idea is that as long as you execute this long enough, you're gonna get enough statistics to know where most of the time is being spent. So let's see an example of a tracing profiler. So here we have a piece of code that is just like a really simple re-implementation on grep done in Python. And what we want to check is what is the bottleneck of this program. Like we're just opening a bunch of files, trying to match this pattern, and then printing whenever we find a match. And maybe it's the regex, maybe it's the print, we don't really know. So to do this, in Python, we have the C profile. And here is I'm just calling this module. I'm saying I want to sort this by the total amount of time that we're gonna see briefly. I'm calling the program we just saw in the editor. I'm gonna execute this 1,000 times. And then I want to match, like the grep arguments here is I want to match this regex to all the Python files in here. And this is gonna output some, this is gonna produce some output that we're gonna look at it. First is all the output from the greps, but at the very end, we're getting output from the profiler itself. And if we go up, we can see that, hey, we spent, by sorting by like, we can see like the total number of calls. So we did 8,000 calls because we executed this 1,000 times. And this is the total amount of time we spent in this function, cumulative time. And here we can start to identify kind of where the bottleneck is. So here, this built-in method IOOpen saying that, oh, we are spending a lot of the time just waiting for reading from the disk. Or there we can check, hey, a lot of time is also being spent trying to match the regex, which is something that you will expect. One of the caveats of using this tracing profiler is that, as you can see, here we're seeing our function, but we're also seeing a lot of like functions that correspond to built-in. So like functions are like third-party functions from the libraries. And as you start building more and more complex code, this is going to be much harder. So here is another piece of Python code that, don't read through it. What it's doing is just grabbing the course website, and then it's printing it's parsing it, and then it's printing all the hyperlinks that it's found. So there are like these two operations. It's like going there, grabbing the website, and then parsing it, and printing the links. And we might want to get a sense of how those two operations compare to each other. And if we just try to execute the C profiler here, and we're going to do the same, this is not going to print anything. And I'm using a tool we haven't seen so far that I think is pretty nice. It's stack, which is the opposite of cat. This is going to reverse the output, so I don't have to go up and look. So we do this, and hey, we get some interesting output. We're spending a bunch of time in these built-in methods, soccer getter info, and like create dynamic, and method connect, and POSIX. Like nothing in my code is directly calling to this function. So I don't really know what is the split between the operation of making a web request and parsing the output of that web request. So for that, we can use a different type of profiler, which is line profiler. And the line profiler is just going to present the same results, but in a more humanly readable way, which is just, oh, for this line of code, this is the amount of time things took. Yeah, of course. And so it knows that it has to do that. We have to like add a decorator to the Python function. We do that. And as we do that, we now get slightly cropped output. But the main idea, we can look at the percentage of time. And we can see that making this request get operation took 88% of the time, whereas parsing the response took only 10.9% of the time. And this can be really informative, and a lot of different programming languages will support this type of line profiling. Sometimes you might not care about CPU. Maybe you care about the memory or like some other resource. Similarly, there are like memory profilers. In Python, there is memory profiler. For C, you will have Valgrind. So here's a fairly simple example. We just create this list with 1 million elements. That's going to consume like megabytes of space. And we do the same, creating another one with 20 million elements. And to check what's the memory allocation, how it's going to happen, and what's the consumption, we can go through a memory profiler, and we execute it, and it's telling us the total memory usage and like the increments. And we can see that we have some overhead because this is an interpreted language. And then when we create this like million this list with 1 million entries, we're getting this many megabytes of information. Then we're getting another 150 megabytes. They were freeing this entry, and that's decreasing the total amount. We're not getting a negative increment because I'm bugging probably the profiler. But if you know that your program is taking a huge amount of memory and you don't know why, maybe because you are kind of copying objects where you should be doing things in place, then using a memory profiler can be really useful. And in fact, there's like an exercise that will kind of walk you through that, kind of comparing an in-place version of Quicksort with like a non-in-place that keeps making new and new copies. And if you're using the memory profiler, you can get a really good comparison between the two of them. Any questions so far with profiling? Yeah, go ahead.
Is the memory profiler running the program in order to get that?
Yeah, like I think you might be able to figure out like just looking at the code, but as you get more and more complex, for this code at least, as you get more and more complex programs, what this is doing is running through the program and like for every line at the very beginning is looking at the kind of the heap and saying, oh, what are the objects that I have allocated? Oh, I have 7 megabytes of objects. And then goes to the next line, looks again, it's like, oh, now I have 50. So I have now added 43 there. And again, you could do this yourself by kind of asking for those operations in your code every single line. But that's not how you should be doing things, since people have already kind of written these tools for you to use. As it was the case with, Control V. As it was the case with strace, you can kind of do something similar in profiling. Like you might not care about the specific lines of code that you have, but maybe you want to check for outside events. Like you maybe want to check how many CPU cycles your program is using, or how many page faults is creating. Maybe you have like bad cache locality, and that's being manifested somehow. So for that, there is the perf command. And the perf command is gonna do this, where it's gonna run your program, and it's gonna kind of keep track of all these statistics and report them back to you. And this can be really helpful if you are working at a more low level. So we execute this command, which I'm gonna explain briefly what it's doing. And it's this stress program is just running in the CPU, and it's just a program to just hog one CPU and like test that you can hog the CPU. And now if we Control C, we can go back and we get some information about the number of page faults that we've had, or the number of CPU cycles that we utilize, and other useful metrics from our code. And even for some programs, you can look at what the functions that were being used were. So we can record what this program is doing, which we don't know about because it's kind of program someone else has written. And we can report what it was doing by looking at the stack trace, and we can say, oh, it's spending a bunch of time in this random R standard library function, and it's mainly because the way of hogging a CPU is just creating more and more like pseudo random numbers. And there are like some other functions that have not been mapped because they belong to the program, but if you know about your program, you can display this information using more flags about perf. And there are really good tutorials online about how to use this tool. Oh, one more thing regarding profilers is, so far we have seen that these profilers are really good about aggregating all this information and like giving you a lot of these numbers so you can optimize your code, or like you can reason about what is happening. But the thing is, humans are not really good at making sense of lots of numbers. And some humans are like more visual creatures, and it's pretty much easier to kind of have some sort of visualization. Again, like programmers have already thought about this and have kind of come up with solutions. A couple of popular ones is a flame graph. A flame graph is a way of a sampling profiler. So this is just running your code and taking samples. And then on the y-axis here, we have the depth of the stack. So we know that the bus function called this other function, that this called this other function, so on and so forth. And on the x-axis is not time, like it's not the timestamps, like it's not this function run before, but it's just time taken, because again, this is a sampling profiler. We're just getting small glimpses of what was going on in the program. But we know that, for example, this main program took the most time because the x-axis is proportional to that. And they are interactive, and they can be really useful to identify the kind of the hotspots in your program. And another way of displaying information, and there is also an exercise on how to do this, is using a call graph. So a call graph is going to be displaying the information, and it's going to create a graph of which function called which other function. And then you get information about like, oh, we know that main called this person function 10 times, and it took this much time. And as you have a larger and larger programs, looking at one of these call graphs can be useful to identify which is calling, like what piece of your code is calling this really expensive like I/O operation, for example. With that, I'm gonna cover the last part of the lecture, which is that sometimes you might not even know that like what exact resource is constraining your program. Like how do I know how much CPU my program is using JavaS? Kind of like quickly looking at like how much memory. So there are a bunch of really nifty tools for doing that. One of them is HStop. So HStop is like a interactive command line tool, and here is displaying all the CPUs this machine has, which is 12. It's displaying the amount of memory. It says like I'm consuming almost a gigabyte of the 32 gigabytes the machine has, and then I'm getting all the different processes. So for example, we have CSAT, SQL, other processes that are running in this machine, and I can sort through the amount of CPU they are consuming or through the priority they're running at. We can check this, for example, here we have the stress command again, and we're gonna run it to take over 4 CPUs and check that we can see that in HStop. So we dispatch those 4 CPU jobs, and now we have seen that like now we have, beyond the ones we had before, now we have these 4, there we go, like these 4 stress minus C commands running and taking a bunch of your CPU. And even though you could use a profiler to get similar information to this, the way HStop displays this kind of in a live interactive fashion can be much quicker and much easier to parse for you. In the notes, there's a kind of a really long list of different tools for evaluating different parts of your system. So there might be tools for analyzing the network performance, tools about looking about the number of I/O operations, so you know whether you are saturating the reads from your disks. You can also look at what is the space usage, which I think here like 7, yeah. So NCDU, like there is a tool called DU, which stands for disk usage, and we have the -H flag for human readable output, and I think we can do videos, and we can get output about the size of all the files in this folder. Did I do control? No, I think I did control P. Yeah, there we go. And there are also interactive versions, like HStop was an interactive version. So NCDU is an interactive version that will let me navigate through the folders, and I can see quickly that, oh, like we have, this is one of the folders for the video lectures, for the video lectures, and we can see there's like, oh, there are these 4 files that have like almost 9 gigabytes each, and I could quickly delete them through this interface. Another neat tool is LSOF, which stands for kind of list of open files. Another pattern that you might encounter is some process is using a file, but you don't know exactly which process is using that file. Or similarly, some process is listening in a port, but again, like how do you find out which one is? So to set an example, we just run a Python HTTP server on port 444, running there. Maybe we don't know that that's running, but then we can use LSOF. Why is not running? Yeah, we can use LSOF, and the thing is, LSOF is gonna print a lot of information. You need like pseudo permissions because this is kind of I'm gonna ask for like who has all these items. And since we only care about the one who is listening in this 444 port, we can ask grep for that. And we can see, oh, there's like this Python process with this identifier that is using the port. And then we can kill it. And that terminates that process. And again, there's a lot of different tools. There's even tools for doing what is called benchmarking. So in the Cell Tools and Scripting lecture, I said like, oh, for some tasks, like FD is much faster than find, but like, how will you like check that? Well, like I can test that with hyperfind, and I have here two commands, one with FD that is just like searching for JPEG files, and the same one with find. And if I execute them, it's gonna kind of benchmark these scripts and give me some output about how much faster FD is compared to find. So I think that kind of concludes, yeah, like 23 times for this task. So that kind of concludes the whole overview. I know that there's like a lot of different topics and there's like a lot of perspectives on doing these things, but kind of again, I want to reinforce the idea that you don't need to be a master of all these topics, but more that to be aware that all these things exist. So if you run into these issues, you don't reinvent the wheel and you kind of like reuse all other like programmers' time on that. Given that, happy to take any questions related to this last section or anything in the lecture.
Is there any way to sort of think about how long a program should take? You know, if it's taking a while to run, you know, should you be worried, or depending on what you're doing or how fast your computer is, you should be like, oh, let me wait another 10 minutes before I, you know, start looking into why it's taking so long. Okay, so
the task of knowing how long a program should run, I think, is pretty infeasible to figure out. Like, will depend on the type of program. Depends on whether you're like making HTTP requests or you're reading data. One thing that you can do is if you have like, for example, if you know you have to read 2 gigabytes from memory, like from disk, and load that into memory, you can kind of make back of the envelope calculations. So like, oh, that shouldn't take longer than like X seconds, because this is how things are like set up. Or if you are reading some files from the network and you know kind of what the network link is, and they are taking, say, 5 times longer than you would expect, then you could try to do that. Otherwise, if you don't really know, like say you're trying to do some mathematical operation in your code and you're not really sure about how long that will take, you can use something like logging and try to kind of print intermediate like stages to get a sense of like, oh, I need to do 1,000 operations of this, and 3 iterations took 10 seconds, then this is gonna take much longer than I can kind of handle in my case. So I think there are ways. It will again like depend on the task, but I think like given all the tools we've seen, you probably have like a couple of really good ways of tackling that. Any other questions?
You can also do things like run htop and see if anything is running.
Mm-hmm.
Like if your CPU is at 0%, something is probably wrong.
Okay. There's like a lot of exercises for all the topics that we have covered in today's class, so feel free to kind of do the ones that like are more interesting. We're gonna be holding office hours again today. Just a reminder, office hours, you can come and ask questions about any lecture. Like we're not gonna expect you to kind of do the exercises in a couple of minutes. They take kind of a really long while to get through them, but we're gonna be there to kind of answer any questions from previous classes or even not related to exercises. Like if you want to know more about how will you use Tmax in a way to kind of quickly switch between panes, anything that comes to your mind.